Good afternoon, everyone. I hope you had a great lunch, and I would like to welcome you to It's About CPU Time, the dark art of benchmarking. Before we begin, I want to stress that we will be looking forward in this talk. We will not be looking backwards.
But first, let's take a look backwards in time. So once upon a time, there were script limits.
And when there were script limits, we had, in a trigger context, up to 200,000 lines of code per trigger context, and 1 million lines of code in an asynchronous context.
Now this limit applied to namespaces. So if you were an ISV developer, this limit was your limit and your limit alone. Additionally, if you were just writing code in an org, so if you were writing just custom code in an org, you also had your own 200,000 line script limit.
So what this meant is, back in the days when you had a limit of 10 managed packages, 10 namespaces in an execution context, each one having 200,000 lines of script, you could conceivably have up to 1.2 million lines of code executing in an execution context. Now, there were some consequences to this that some of you may remember. One is, people wrote some really ugly code. You may remember if you had to do a complex condition with 7 or 8 conditionals, you would cram them all into one really convoluted, complex line, because that way it would only take one line of script.
And then also, if a script limit occurred, it was clear that you were the blame. Your application was the one causing the error. It's your fault. You have to fix it.
And because each one of us had our own bucket of lines of script, we tended to really obsess over the efficiency of our code and not worry about what was going on in other packages and so on. And this all changed in API 29, Winter 14, when they switched to CPU limits. No more script limits! And there was cheering and joy and rejoicing.
These script limits were based off of measurements that Salesforce did at the time that was going to be plenty of time for everyone.
Right. They ran all of the orgs, and they figured out how much time was being used, and they allocated 10 seconds for a trigger context, 60 seconds for an asynchronous context, and pretty much all code ran OK.
But notice here, there's a few key differences to this limit. One, this limit applies to not only Apex code, but declarative as well. So workflows, lightning processes, validation rules, formulas, all of this counts towards the 10-second limit. In addition, that limit is shared across everything running in the org at the time. It's not managed package specific.
Still, 10 seconds, plenty of time. 60 seconds, that's a lot of CPU time. Until you remember that a lot of things we do in batch. So for example, if you have a batch of 200 records, that 10 seconds in a trigger context goes down to 50 milliseconds of processing per record, which is still generous, but not quite as generous as 10 seconds.
We run into a problem, though. What if you're selecting 1,000 records and you're looping over 1,000 records? Now you're down to 10 milliseconds. If you have a SOCO query and you're selecting 50,000 records, the maximum number that you can query in a SOCO query, you're down to 0.2 milliseconds per record.
And you can't do a whole lot in 0.2 milliseconds. So what this tells us is that in reality, CPU time is a thing. It is an area that you absolutely can run into trouble, especially when you start doing bulk and batch operations. So what are some of the consequences of this change? Well, one consequence is that fewer developers really obsess over optimization. Because when you're developing code, you don't have a whole bunch of other things going on in an org. You have that whole 10 seconds or 60 seconds all to yourself. So there's sort of a tendency to not pay as much attention while you're doing developing.
Customers that have a lot of managed packages in their org, especially managed packages that all operate on the same object, so if there's a lot of managed packages that all work off the lead object, these customers might be more apt to running into these script limits. And then also, another consequence is that code that once passed this script limit rule may no longer suddenly pass this CPU limit rule. We may run into exceptions where there was once no exceptions occurring.
Right. Before, you would have your script lines, and that's what you had, and as long as your code could run in that available number of script lines, you were good if you were an ISV, if you were distributing a package. But now things can come along later that can cause problems. For example, what happens if you have an application, two applications, and one uses 9.5 seconds in an execution context, and another uses 1 second. And poor application B has the misfortune to run after application A. Well, application B is going to trigger a CPU time limit, and it's going to get the blame, even though application A is the one that really burned up that CPU time. And which one is going to get blamed is going to depend purely on which one, the order of execution, which of course we don't know.
And it's currently not possible, looking at the debug log, to know what is actually using the CPU time.
So we're going to make some assumptions during this talk. One assumption is that it is still important to obsess over optimization. Another assumption we're going to make is that it's going to be difficult for many of you to do so, because you have all of the time available while you're developing, and it's sort of hard to go to your manager and say, well, it passes the test, it's ready to ship, we have code coverage, it's all good. I want to spend another 10 hours optimizing my code just in case they have other packages in their org. And they'll say, no, right? We're already getting paid by the customer. So we know that it's going to be hard to care about optimization the way it was before, but we're going to talk about it anyway because it's interesting and it's fun and it's important. That said, welcome to the dark art of benchmarking.
Now, Mark Twain has this famous quote. He says, "There are lies, damn lies, in computer software benchmarks."
Check it out. It's in a Connecticut Yankee in King Arthur's court. That said, we are going to lie to you today. I guarantee you this will be the least accurate session in the entire history of the Dreamforce conference. And that's because benchmarking is hard.
It's really, really easy to get the tests wrong.
It's really hard to avoid side effects while you're benchmarking.
You can't control background operation timing like garbage collection.
And because of that, your timing can't even be trusted. If you look at debug logs, sometimes you're going to see some really strange results.
Internal caching and optimizations can distort your results.
Your overall system performance, and thus the results you're going to get, are going to vary by time of day, by momentary load, whether it's a weekday or a weekend, a holiday, and so on.
Because of that variation in results, tests run even seconds apart can vary up to 10 to 20%.
And the results can change with every patch and release. In fact, I would bet that the results we show you today that we measured like a couple of weeks ago are probably not even accurate today. And they're certainly not going to be accurate in a couple of weeks when Windows 17 comes out.
Also, we're going to teach you how to benchmark code. And to benchmark code, you need to debug. And debug logs themselves cost CPU time.
It's sort of like Heisenberg's uncertainty principle. The very act of trying to do the measurement for benchmarking changes the results of the measurement. So the results we give you are not going to be accurate, and that's why it's so important to know how to benchmark, because it's going to be essential when you're figuring out what are the best design patterns to use. You need the ability to benchmark your own code based on the state of the system when you're doing it. So that said, we're going to start out, my turn first, and talk about how do you benchmark code. I get the easy part. Just wait till you see what he's going to come up with. Benchmarking code is actually pretty simple. It always looks something like this. You have a function where first you initialize any variables that you're going to need. In this example, we're going to compare field access, static versus dynamic apex. That's sort of an interesting thing. Which one is faster and by how much? So we're going to grab a contact that we can do our field access on that. We're going to initialize a couple of variables, and right before this loop, we're going to capture the current CPU time. Then there's a loop with a very large number in it, and I'm going to talk more about that in just a second. That's where we're going to put what we measure. After that, we're going to do a system debug statement where we display the CPU time used. We subtract the current CPU time from the value that we captured earlier. Notice that we use logging level.error. The reason we do that is because we want to use the coarsest possible debug capture the least amount of information, because every system debug statement eats up CPU time. What a loop looks like is something like this. First, we have a loop where we have a very simple assignment, one variable to another. And in this particular case, it uses about 0.25 microseconds. So 250 milliseconds for the whole loop divided by 1,000,000. Now, that 0.25 microseconds is not the time to do a single assignment. That's the time to do the entire loop with the assignment. So we want to factor out that overhead. Next, within the loop, we add 10 more assignments. Do the measurement again, and in this case, it came out about 600 milliseconds. Subtract the 250, divide it by the 10 operations, and we discover that a simple assignment takes about 0.035 microseconds, which is insanely fast. And it's a testament to the power of the platform on which Salesforce is running. Those are some amazing times. Now we go and we take the exact same thing, but we're going to replace those 10 assignments with field access. Perform the same operation. In this case, it takes 6,000 milliseconds. Subtract the two, do the math, and it comes out to 0.58 microseconds for a field access. Now we pick that number, we pick the million here. You want to pick a number that's big enough so you're using a significant amount of the available CPU time. In this case, you see we're using 6,000 milliseconds, 6 seconds out of the 10,000 available. That gives us sort of our best resolution. You want to be somewhere in the middle there in order to get the most accurate information. Too short, and you're not going to have any precision. Too many loops, too long, and you're going to exceed your CPU time, which basically gives you no information at all. When we went to dynamic apex, where we're using the sObject.get statement with the field name provided dynamically, you notice that the loop count was reduced to 10,000. When we tried to do it at 1,000,000, it exceeded CPU time limits. We find that it took 1805 milliseconds minus 2.5, not 250 anymore, right? Because we changed our loop from 1,000,000 to 10,000. So our loop overhead went from 250 to 2.5. And we discover that it's 18 microseconds for dynamic apex. So we've done this benchmarking, and from this we can draw some conclusions. The assignment from a static field reference is about 20 times slower than a simple variable assignment. The assignment for a dynamic field reference is about 30 times slower than a static reference. So what this tells us is that as developers, if you're going to do even 2 field accesses, especially dynamic apex, it makes sense for you to assign it first to a temporary variable and then to access the temporary variable. You can get significant performance. So imagine, for example, you're looping through a record and you've built bulk safe code so you can go up to 200 times through it, and you're accessing a field dynamically. You certainly don't want to do it more than once if you can avoid it, because it eats up a ton of time. Knowing how to benchmark code, we sort of went on a hunt to look for a few other interesting things. For example, we looked at describe statements. Some of you may remember that describe statements are cached now. It used to be that every time you would do describe statements, you would want to cache it yourself, and Salesforce decided, hey, our customers are doing it anyway, let's make it easy, let's cache it for them. A simple get describe on an account to get the describe information for an account, as you can see, is pretty quick. It's 1 millisecond the first time through, 0.015 milliseconds for all subsequent calls. So it makes sense, anytime you need it, to just call that. There's no real need to cache. But let's say you're using get global describe. 11 milliseconds the first time and 2 milliseconds subsequent, and that's on a pretty much clean dev org. Now you're getting into some more significant times. And on a larger org, you can see that it's org size dependent. An org with 2,176 objects was 200 milliseconds the first time, which is huge, and 11 milliseconds subsequently. So the last thing you're going to want to do is put that call in a loop, right? So if you're doing a loop with 200 records, you don't want to call get global describe each time. You want to cache it yourself, even though they're doing caching for you. It's important, especially if you're an ISV partner doing a managed package, to remember that this is a good example how some of the things you're doing, the timing that you're measuring on your development system may not reflect the times that you would see on the customer system. Other things we found, if you're doing mathematics, the native floating point format in the Salesforce database is decimal. However, doubles are a whole lot faster. So if you're going to be doing any significant amount of math, switch over to doubles, convert to doubles, do your math there, and then convert back. And the reason for that is that doubles are supported in hardware. So they're significantly faster than decimals that have to be processed in software. Also took a look at iterating through an array. We iterate through arrays all the time. Usually we'll use the var x:array format, and we're just sort of curious. Which is faster, that or a loop? Sort of intuitively thought the iteration would be faster, but it's not. This rather surprised me. 4 microseconds per iteration when using an iterator, but when using a counter type loop, it's only 2.5 microseconds, and if you move the size calculation into a temporary variable outside of the loop, it's down to 0.75 microseconds. Now you might be thinking, does this mean I should start using counters for my loops instead of iterating? Absolutely not, because 4 microseconds is still really, really fast. And even if you're looping through it 200 times, it's like you're going to get up to, what, 800 microseconds, less than a millisecond? This is a case where I would stick with the preferred design pattern that you want rather than focusing on benchmarking.
Now, we took a look at other methods as well. The JSON serialize method, for example. The interesting with that method is you pass a parameter into it that you want to serialize into a JSON string. If you're benchmarking Apex and you're benchmarking this method, for example, it's going to be pretty quick if you're just serializing a simple string, serializing in about 73 microseconds. But it's really dependent on the data that you're passing into the method. If you're trying to call serialize on a list of 400 strings, you're up to 7 milliseconds of CPU time for that method. So it's kind of like the getGlobal describe. You have to know what you're actually passing into it or what is actually existing in the org to know what kind of CPU time you're going to see.
Your turn.
My turn. Great. So Dan did a great job at explaining how to benchmark Apex code. But how do you benchmark declarative? We all know now that with CPU time limits, declarative also counts towards these limits. This is the definition taken from Salesforce. Time spent evaluating formulas for validation rules or workflows are counted towards your limit. If your validation rule or formulas have poor logic, it's no less detrimental than poor logic written in Apex. So what is poor logic in workflow rules? How do you benchmark workflow rules? Well, let's dive in and take a look. So in the example here, I'm setting up a basic workflow rule. It does a few different operations. Specifically, we're just looking on the lead object. We're looking at 10 fields on the lead object to see if they're blank. If they're blank, we're just doing 10 field updates. Now, benchmarking workflow rules is really hard. It's much different than benchmarking Apex for one specific reason. We can't insert a million records. We can't insert 10,000 records at a time, a million records. We're gonna, that's just not possible in Salesforce right now. So unlike in Apex where we're able to loop over an array a million times, we're limited with what we can test. So for this workflow test, we're going to insert 200 lead records, but we want to make the workflow complex enough so that we have significant data. Remember, Dan talked about a few moments ago where we want to hit, between the middle ground of your CPU limit. If we just have a very, very basic workflow rule here and we're inserting 200 records, we're going to have very low CPU usage, so we're not going to have significant data. Now, just because we're benchmarking workflow rules doesn't mean we don't need code. We need an after insert and after update trigger. This trigger will run and call this block of code here. And notice that the code is very, very basic. We don't want much code when we're benchmarking workflows because we don't want the code interacting with our results. It's pretty straightforward. It's kind of similar to how you would benchmark Apex. We're marking the CPU time. Notice we're marking the CPU time in an if statement, so if it's null. So this will be when we're doing the after insert. We're marking the CPU time. And then at the very end, when your after update is called and this method is called again, we're outputting the elapsed time. So it looks something like this. You're inserting 200 records, your after insert trigger runs, the workflow rule runs, and because the workflow rule processes field updates, the after update trigger is going to run, and because that block of code is running in your after update trigger, it's going to mark the end CPU time. And all it's doing in your system.debug remember to do system.debug logging level of error, it's outputting the difference between the end time and the start time. And that is the total CPU time that it took for that workflow to run. Now, I will caution you to, whenever you're testing this, do it on an object where there's not other triggers or workflows operating on that object. It's probably even preferable to work on, if you're in an org with a lot of different objects or a lot of different triggers, just create your own custom object and work on that to do your benchmarking. So the definition says that it's no less detrimental. Well, when I was doing the testing for declarative, I also wanted to compare it to Apex. In addition, I also wanted to compare the different declarative operations. So I'm going to test workflows, processes, and also the Apex equivalent code. This just shows a quick example. This would be the Apex equivalent code of the workflow rule. It's running in a before inserts trigger. It's simply looping through all the leads that are being inserted, and if the fields are blank, then we're setting the fields that we want to change. It's the same exact as the workflow rule. Now we have a process. Again, this process is the same exact scenario as the workflow rule. We are inserting 200 leads, and as leads are coming in, we are looking to see if certain fields on the lead are blank. If they're blank, we're going to update the lead fields. Seems pretty straightforward for a process. So let's take a look at the results. The Apex code and the workflow rules perform about the same, between 2 to 3 milliseconds per lead record when you're looping over using the workflow rule or using the Apex code. What was really surprising to us is to see how inefficient the process seemed to be. It was using 8 milliseconds per lead, just to process that simple scenario that we were examining. So they weren't joking. The definition is correct. Declarative definitely uses CPU time. And also, it looks like processes are much less efficient, at least in the scenario we tested, than workflow rules. So we did some more investigation as well. Some other interesting findings. Sending emails is really CPU intensive. Just with a simple field merge template with 10 fields was adding up to 15 milliseconds per email. That's 3 seconds of CPU time if you're processing 200 records. Alternatively, we discovered that inserting task records, at least the scenario we were using, was only using about half a millisecond per record. Now be warned, if you have other processes or triggers that work off the task object, that may be higher. But if you just don't need to send the email and need to assign a user a task instead, maybe try doing that instead. Validation rules. So validation rules also count towards CPU time. So if you're inserting or updating records and you have 10 validation rules, each with 10 different functions in the validation rule, that alone is going to eat up 600 milliseconds of CPU time if you're inserting or updating 200 records.
Now, you've seen that Apex can use CPU time, and you've seen that Declarative can use CPU time. But it's nothing compared to the amount of CPU time you can burn up when the two of them cooperate and work together. And here's a simple example that illustrates it. Imagine you have an org with 3 applications, each of which is using 2 seconds in an execution context. All is good, all is happy, no problem. Along comes someone who adds a workflow field update, which causes those 3 applications to re-trigger. It hits A again, another 2 seconds, B, another 2 seconds, and boom, you hit a CPU time limit. C doesn't even have a chance to run. So even a simple declarative change can take a properly running org and bring CPU time limits into play.
That was with workflows, but processes also operate the same way. Poor application A here is only using 0.1 seconds of CPU time, but they're getting the blame for the CPU exception. The interesting thing with processes that we discovered, if you take a look here, we actually hit the 10-second CPU limit when we were in the middle of the process, but no CPU exception was thrown during that process. It was thrown after the process when we were in the Apex code. So that was interesting. Let's try to illustrate a process that takes a really, really, really long time to run. So this process here always runs when leads are inserted. In this example, we're going to insert 400 leads. And all it does is calls an invocable method in Apex that just takes a really, really long time to run. And then it also updates leads. This is the really, really, really long method that runs. Do not do this ever. This is not something you should do. We are serializing a very large array for every single record that comes through. So when this method is called from the process, we're going to have 200 records that come through. Remember, we're inserting 400, but we only process 200 at a time. So the for loop is going to run 200 times and serialize a large array, presumably 200 times. So what could possibly go wrong? Well, we run into a CPU exception. If we take a look here at the debug logs to see where we're hitting our CPU exception, we see that it looks like it happened on line 92 of the handle lead trigger method in the lead trigger handler class. So perfect. We know where the error happened. Let's take a look. Well, this class is pretty basic. We're just outputting CPU time usage, not really doing anything in loops or anything of that nature. So it seems pretty safe. Let's take a look at another section of the debug log. Let's turn on Apex profiling and see where that CPU time usage is actually happening. If we notice, 15,000 milliseconds is being used by the serialize method. That's the method that we're calling the for loop. So 200 times we're calling this serialize method. And 15,000 microseconds is actually 15 seconds. Sometimes, we didn't mention this yet, I don't think, but Salesforce is generous in this CPU time limit. It's probably one of the only limits I know of that is kind of a soft limit. You can go over the 10-second limit and not actually see an exception happen. In our testing, we were seeing exceptions happen after about 15 seconds. But if we take a look, it's really interesting because we see here that it executed 83 times. Now, if we're inserting 400 records and we're processing 200 at a time, I would have expected to see this execute 83 times.
200 times.
Yes, 200 times, not 83 times. Especially because the code that threw the exception happened after the process. So what happened? It seems as though the process aborted the action silently, went along, did the other action, and then your after insert trigger ran to process the next 200 leads. And that's where the CPU exception happened. So that trigger was blamed for the error, but the error actually, or the reason we ran into the error to begin with is because of this action that took a really, really long time to execute and was aborted silently. The nice thing here is that all your records that you inserted are rolled back, so nothing stays in the system. What if we were just inserting 200 leads and you didn't really have much else going on that lead trigger? We just have this process. Your after insert trigger runs, then your processes run after your triggers. So the process runs, calls that really, really long running method, aborts it silently, so it only ran 83 times out of 200, updates the leads also, it moves on to the next action, and then your debug log is successful. No errors actually occur. Records are not rolled back. So that was very interesting to find. If there's any process builder PMs here today, I'm sorry. So no rollback has happened, no CPU timeout is detected here. Just a very interesting scenario that we discovered.
So what can you do to prevent death by interaction? As an Apex developer, you can certainly use the getCPUTime statement during your code to see if you're beginning to run up against limits. And if you are, you have the option of either aborting or perhaps moving and triggering an asynchronous process so that you can get another execution context. Another really important approach is to use somewhat more advanced architectures, where, especially in triggers, you keep track of reentrancy using static variables, so that if your trigger is re-triggered, you can quickly determine, you know that you're in a reentry situation that was potentially brought about by other Apex or workflow, and you can hopefully identify if you can exit quickly. Because if you can exit quickly, you'll be using less CPU time, which reduces the chance that your code is the one that's going to raise the CPU time exception and get the blame. But it's important to accept the fact that no matter what you do, any code you write, whether it's a managed package or your own code, is at risk of being blamed for CPU time limits, of raising a CPU time limit exception, both now and at some arbitrary time in the future as the org changes. So what can we conclude from this? What we have now is a race. On one hand, you have an increase in the size and complexity of applications. While it's true that when CPU time limits first came out, they checked to make sure that they granted enough so that all existing code could run, with that generous available limit, people have built bigger and more complex applications. So as that happens, we have a force in the direction of using more time. And also, because developers tend to have their own pool and see the entire available CPU time, there is, I believe, an increase in the amount of unoptimized code that is out there, because there is no great need to obsess over optimization as there was in the days of script limits.
Now, on the other side, we have the Salesforce platform, and Salesforce is continuously improving their platform, and it's possible that at some release in the future, maybe we'll see an increase in CPU time limits. Or improvements to the Apex compiler will make it so that your code is running more efficiently and taking up less CPU time.
I believe there's a session here at Dreamforce about a new Apex compiler coming. I have no idea what it is, but I promise you it will invalidate everything we said here today.
Remember, we're lying to you.
That's right. Now, there is some good news, and that is that optimization as a developer is really fun. I mean, we had an enormously fun time exploring and experimenting, and it has already impacted the code that we write. Also, sometimes figuring out what is wrong, it's like detective work, it can be a lot of fun.
Unless you're getting the blame for it.
It's true. And you have great job security as these bugs come in.
Unless you keep getting that blame.
I invite you to check out my book on advanced Apex programming, where I talk both about benchmarking and some of the design patterns that address interaction. I want to point you to Robert's GitHub, where you can find the benchmarking. And I want to just take a moment and acknowledge Robert is a senior developer at Full Circle Insights and is doing absolutely pioneering work in this space. I don't think anybody has ever seen some of the things we've shown you here today. So it's really been exciting as we're working on this for, every week you come by. So look what I found now. It's like, oh, wow, can we put this in the talk? And so on. And I also invite you to check out searchtheforce.com, which is a Google search engine driven Salesforce-specific search engine. So basically, instead of having to, when you're searching for things, which we do all the time, instead of having to type Salesforce, Apex, and so on, you can just go there and know that it's searching all the Salesforce domains, Salesforce blogs, pretty much all the Salesforce content we could find. Makes life a little bit easier. And with that, we have 6 minutes for either Q&A or if you have any of your own horror stories that you have to share. And I don't know if there's a microphone. Is there a microphone? I don't know if there's a microphone, but I'll try to hear what you're saying.
I have a question about scenarios where, let's say you run a unit test at time X, and then an hour later you run it. First time it fails due to CPU limit, an hour later. What are the variables impacting time-related failures?
What are the variables that relate to time-related failures on unit tests, where one will fail with a CPU time limit now versus later?
Yes.
What a great question.
I've got documented proof.
I believe, in theory, a particular piece of code will use the exact amount of CPU time limit every time. But I don't think that's true. I haven't seen that to be the case. It varies quite a bit.
It varies a little bit, yeah.
So I don't know. It's a good question.
Because you would think, when you look at
Right.
It's the sum of all the samples.
Right. You would think that the timing measurements coming from the debug logs are accurate and would be reproducible.
Which measure down to
Right.
machine.
I know, you would think so. Maybe we're not the only ones who are going to lie to you today.
The other thing I wanted to just share was, you mentioned the get describe
Yeah.
usage, or get global describe. One way to address that is just take advantage of the fast loader, doing that at load time, get describe, and kind of encapsulate.
Right, he's describing a great design pattern where you initialize a static variable so that as soon as the class is instantiated, it calls get describe and basically caches that information, right? Here's the catch with that, of course, is that now you're taking heap space, right? So if you're tight on heap space, that could potentially be a problem area. We're always trading off limits, right? Yes, sir?
I just want to make an observation. We've got code out there that runs fine for months and months and months, and suddenly we'll get a sporadic CPU limit. There's something happening on the platform. Maybe the org is being overloaded at that moment, and you know the context of something's happening in the background that code execution isn't happening.
Right. What you described is you have code and it's working fine and everything's fine, and then all of a sudden you get sporadic CPU time limits and you don't know why, right? And yeah, how many people have run into that yet? You're starting to see, oh boy, it's worse than I thought. What happens is you have an org that's sort of in a steady state and people are working with it, and one day some admin decides to import 200 records or bulk import 1,000 records, and boom, everything blows up, because now instead of having that 10 seconds each time, and very few developers are really building bulk safe code, unfortunately. So yeah, it's a real thing. Back there.
Yeah.
Yes.
So you mentioned process field updates, right? Does it mean that workflow field updates are more faster than process builder field updates?
He's asking if workflow field updates are faster than process builder field updates.
I don't know about the field updates. The process the example was the update. So it seems that way. Our testing was on the workflow rule in the process, simply looking over if certain fields were blank and then updating fields.
Right.
So I guess I didn't go that far. I don't know if it's the formula that's taking a long time to evaluate or the update itself.
Right. So
That's a good question.
to give you an idea, when we were doing this testing, we actually would, in many cases, use 10 identical workflows to do measurements. But what you would do is you would take, and you can try this with the example, and change the number of field updates. You maybe go to multiple field updates versus one field update to figure out how much of the time is being spent in the formula and how much of the time is being spent in the field update. Benchmarking is really hard. Back there. Yes.
In addition to process builder and workflow, did you try flows?
Flows. We didn't try flows.
I don't think we looked at flows so
No.
much.
If you try flows, please let us know. Yes.
When we've done profiling, we found that execute anonymous was a lot slower. We've used visual force pages to trigger the profiling, found some of the results. The actual question, do you have any advice on how to test in a sort of continuous integration context some code that has to be critical that is really fast? So use cases that we obviously code in a shared library, which is going to save all the records. Too far away, and it's too slow, then it's not something they can do anything about. So we need this code to run really fast. And maybe the Salesforce release is going to make it run really slow, we want to spot that in this integration. And how to do it.
So there were 2 points here. One is a lot of our testing was in fact done with anonymous Apex as compared to unit tests. And that's because we too have found that unit tests give you really strange CPU time results. So they are not trustworthy as anonymous Apex or testing from Visualforce. In terms of monitoring performance during continuous integration, I don't know, but I would assume such a thing would be possible, and that you could configure Jenkins or a continuous integration tool to report on the time to execute unit tests and let you know if it's gotten significant. I believe
Yeah, we're out of time.
one more question, since they're not yelling at us yet. Yes, orange shirt.
When you were looking at process builder and evaluating the conditions, and you were looking at this blank certain field, did you guys then look at traversing into related objects and checking is blank on those fields?
We were just looking at is blank on the related fields.
Right. It is a safe bet that related fields are going to take longer. I mean, but how much longer, we don't know yet. Again, the purpose of this talk was to give you the tools on how to do the benchmarking as compared to try to give you a bunch of results, because the results we gave you are all wrong. And with that, thank you very much.
If you guys have more questions, we'll be back there.